So this is Science for Skeptics video. Unfortunately, I don't have much time, so I'm not going to go through all of it. I'm just going to pick out bits and give my thoughts on those parts. I will link the full video in the description so that you can check it out. I suggest you check it out. Yeah, I've got a feeling he's going to add gravity into this at some point. But for now, we'll see where he goes, and I'll give you my explanations for what's going on.
Nothing more, nothing less. You put it on a scale, the number on the scale is the operational weight. Because we're describing weight in this way, the concept of being weightless follows naturally from that. In this example, the people in the aircraft will be experiencing a moment of weightlessness as the aircraft goes into a dive. By accelerating downward towards the ground, the aircraft can be made to simulate a weightless environment where everything becomes neutrally buoyant.
Oh my God.
The people will no longer be held to the ground, and the helium balloon will no longer be pulling taut against the string. But watch what happens right here. As all the people are drifting in a particular direction at the same time. Let's watch that again and keep your eyes on what the helium balloon does during that same drift. As the people are drifting to the left, the helium balloon is drifting to the right. They're moving in opposite directions. So does the zero-G plane...
Okay, so first of all, I'd like to say, great catch. I didn't actually catch that. So for me, the explanation, they are not weightless at all. I know you use the quotation marks with your fingers, but they're not weightless at all. They still have full weight. The weight hasn't changed at all. Okay, now my explanation for what happened there is, for why it went down and for why it goes left and right, is basically, imagine you have balls on the floor, like lots of small balls, all on the floor of the airplane. Okay, now imagine these balls are the air. Okay, so these balls represent the air. We'll pretend there's no balls above them for now, no air above it. And we'll pretend that air just goes in a downward vector for now, just to simplify things. So air just goes down for now, it doesn't go in all directions. Okay, now imagine you accelerate that floor down faster than what the balls fall. So the balls fall at a specific rate, and then you accelerate the floor down faster than what the balls are falling. Therefore, the balls are going to lag behind. So that means the air is going to lag behind. That means that you're going to end up with more dense above, towards the top of the plane, and less dense below. So, because the balls are not able to catch up with the floor, so they get lagged behind because the floor is accelerating down faster than what the balls are falling. Again, the balls represent the air. So you end up with less dense below and more dense above. What do helium balloons do? They go to less dense. What did it do? If it fell and it went to less dense, away from the more dense, as it normally does. So now with the left and right thing, so basically what happened there is, obviously the plane must be accelerating in a direction, and the air is shifting to where the people are shifting. So in this case, going to the left. So then you end up with more dense air, you know, towards the left because it's shifting that way. Because of the acceleration, like in a car, the air will shift. So you end up with more dense one side and less dense the other side. So then the balloon ends up going to the less dense because it's less dense. So that's essentially what's happening there. It's still relative density, nothing to do with weight, nothing really to do with vectors. Again, another way that we can prove this, if somebody had something like tungsten hexafluoride or sulfur hexafluoride, some kind of dense gas maybe that can go down in air, because more dense down, less dense up, even though gas still eventually goes in all directions and that. Obviously that depends on energy and a lot of things. But yeah, if we had something more dense than a helium balloon, more dense than helium, and we had an helium balloon in a container, and we poured this gas, this denser gas, towards the one side, obviously gas goes in all directions, but obviously if it goes in all directions, obviously one of those directions is down too. So you could pour some of this gas, say we have tungsten hexafluoride or sulfur hexafluoride, you could pour that gas to the one side of the balloon in this container and pour it to the one side of the balloon, and the balloon will move the opposite way because it moves away from the more dense, because it's helium. So it will move to where the less dense is. So it will move the opposite way to where you pour that gas at the side of it. So yeah, if you pour the gas at the side of the balloon, it will move the opposite way. That's essentially what's happening here. You don't need any acceleration or anything like this for this to happen. The acceleration is just basically doing the, you know, the pouring for you kind of thing, to speak. It's shifting around the medium, it's shifting around so that it becomes more dense in some places and less dense in other places. And that's essentially, it's not caused by the acceleration. It's the density. The density's changed areas, and it's changed density in different areas. So then obviously the helium balloon reacts to where the less dense is and where the more dense is. Yes, you can say it was caused by acceleration, but that's only because the acceleration caused the density of the medium to change around in different parts of the, you know, plane or whatever. So it's not really to do with acceleration. Again, it's just to do with where the density is and where the more dense is and where the less dense is. So it's still just relative density. The acceleration has just taken out the equation of you actually pouring more dense to one side. It's just done it for you by causing an acceleration. The acceleration causing it. But you don't need the acceleration to cause that. As I said, just pour it to one side and it will go the opposite direction. It's essentially the same thing as what they're doing. They're just not pouring it to the side. They're just using the acceleration to kind of pour it to the side, for lack of a better term. But yeah, let's carry on.
Prove that density has nothing to do with this. Quite the contrary. What we saw was that when the pilot went into the dive and established 0G, everything became neutral, whether it was lighter than air or heavier. But when the pilot accelerated a little bit more, we saw that the people, heavier than air, were thrown upwards towards the ceiling, while the lighter than air balloon was thrown down towards the floor. So what is that?
I have to disagree there. I don't think anybody was really thrown up at all. As I said with the ball analogy, the balls are just lagging behind. The people are technically the same as the balls. They're just lagging behind. The plane's falling faster than what they are. So they're just lagging behind and they appear to go up. Just because technically they are falling slower than what the plane's falling. Obviously they appear to hit the ceiling and things like that, because obviously, you know, if the bottom of the plane moves down a metre, the top of the plane, obviously the ceiling of the plane is going to move down a metre. So yeah, the plane's just falling faster than what they are, essentially. They're not weightless, they're not floating. It's an illusion, it's a trick of the mind kind of thing. A reference frame, whatever you want to call it. But really they're still just falling.
Mean in terms of this equation, our law of relative density? Well, what we saw was that the reaction of the objects was still driven by the difference in density. But by accelerating upward or downward, the pilot was able to somehow modify this k vector. Remember, we measured the k vector. We found in our own kitchens that we got 1.0 grams of force per gram of mass. But what we saw in the flight was that when the pilot went into the dive, accelerating downward, if we were to measure k in that situation, we would have gotten 0. And then there was a point when it got even less than 0, that k became a negative value.
See, he says that it becomes 0 then, or the k, I'm guessing, or the weight, or I think he means the k became 0, but I mean, in this sense he's talking about weight, but to me this has nothing at all to do with weight. I mean, if you wanted to measure the weight, I suppose you could stick a scale to the ceiling and then accelerate down faster so that the people lag behind enough so that they touch the ceiling, and then you can measure their weight. They still have weight, they're not weightless, do you know what I mean? So yeah, this to me has nothing to do with weight. Density is technically every vector. It's just the fact that when you're, you know, not accelerating, the medium pretty much around you is constant. You don't really have more dense to one side or another side, unless like you have wind or things like that. And obviously it won't matter if the object's more dense anyway, because the object would still go down. If the object's more dense than the medium, less dense, obviously it will go up because it wants to go to its, you know, seek equilibrium and go to its own density. So yeah, the vectors for density is pretty much every single vector. It just depends where the density is, and because normally the density all around you is the same, I know they say it's less dense above the object. But again, if the object is more dense, then it'll go down because it wants to go to more dense. More dense is down. And then obviously with a helium balloon, yes, it's less dense above, and yes, that's why it goes above, up, because obviously it's going to its own density, it's less dense, it wants to go up. So yeah, that's essentially what it is. And then obviously left and right, depending on where the density is. And the acceleration, you could say, is what's changing where the vector. But the acceleration is not really changing the vector. It's the density of the medium that's surrounding the object, and then obviously the density of the object that gives you the vector. The acceleration is, as I said before, it's just basically moving the medium around, so then you end up with more dense in different places. So obviously then it can move the less dense. because it's more dense, and it's more dense in some places, so then it, it moves the less dense towards the less dense. That's essentially what's happening. Nothing to do with weight, nothing really to do with acceleration. It's just the fact that they've, accelerated to cause a change in the medium, to cause a change in where the density of the medium is like. So again, nothing really to do with acceleration or weight or anything. So to me, it's still just relative density.
Looked like a very small negative value, which caused the helium balloon to be driven downward while the people were driven upward, moving in opposite directions. So the equation still holds, but we learned something. We learned that this K constant isn't quite constant, is it? It can be affected by an acceleration. And we learned a little something else. You'll recall from the previous video that we had discovered that this K vector carries with it the direction of down, that something in nature wants heavy objects to be pulled downward, and that direction down does not come from the density. It does not come from the relative density. We saw that during this zero-G flight when objects started moving sideways.
So to be honest, I think I've really covered all these points in this now. Yes, he believes it's something to do with weight. Yes, he believes it's something to do with K and the acceleration. As I says, I don't believe it's to do with the acceleration. The acceleration basically just changed the medium around. If you want the same thing to happen, like I says, get a helium balloon, put it in some kind of small container, obviously attach it to the bottom of the container so it don't fly away, obviously because it's going to be in the medium of air, and then just take the lid off the container kind of thing and pour some gas, some denser gas, to the side of the helium balloon. The helium balloon will move away from the denser gas. That is what will happen. And again, you didn't add an acceleration which caused it to go in that direction. So again, it's proving relative density, because you don't need the acceleration for it to happen to cause a sideways vector. Just pour more dense gas to the one side and it will move the opposite way, essentially. So that's what's happening. It's not really nothing to do with acceleration or weight. It's just density and relative density. So yeah. He does, however, come up with a good experiment. I mean, obviously he mentions the balloons in the car, but as I've said, this is essentially the same thing. It's nothing really to do with acceleration. It's just where the density of the medium is. He comes up with an experiment that people can do to measure the angles based on acceleration. Actually, while we're on acceleration, I'd like to talk about the accelerometer. So basically, the accelerometer, you put the accelerometer on the floor. It measures that you, accelerating at 9.81, whatever, something like that. And basically, if you look at the phone on the floor, your phone's not moving, it's not accelerating. But yet the accelerometer says it's accelerating. Now you drop the accelerometer, it reads 0. But yet it's accelerating, you can see it's accelerating, it's moving, it's accelerating. So that tells me that really the accelerometer is no good, because let's for instance say you was in some kind of capsule with no windows, and so you couldn't feel acceleration, you couldn't feel any movement whatsoever, and then let's say you was actually falling out the sky but you couldn't feel it for whatever reason. Obviously you would in real life, but let's for a minute pretend that you wouldn't feel it. Then that accelerometer is not going to be no of help of you. You're going to think you're stationary when really you are coming crashing to the floor, because it's saying that you're reading 0 acceleration when you drop it, when you're falling. So again, I think it's just programmed to say that, because obviously you can clearly see it's accelerating when you drop it, but yeah, that says it's basically stationary, which it's not. So yeah, that's another point, but yeah.
The paper you have. We're expecting a vertical acceleration of about...
I will link this and you can watch it yourself, but yeah. To me,
this tells us that the effect...
Still just relative density, not weight, and no K vector needed. But yeah, let me know your thoughts. Take care and stay safe.